Okay, so now that we have the theory behind how a hypothesis test works, let's actually see how we do a hypothesis test from start to finish. So recall we had the decision rule, and the decision rule is based on the p-value. We're comparing the p-value with alpha. Remember, if p is less than or equal to the significance level alpha, we reject the null hypothesis. If not, we fail to reject the null hypothesis. Suppose the p-value is 0.0237 and our significance level is 0.05. What is our decision? Well, p is less than or equal to 0.0237, is less than or equal to 0.05. So we should reject the null hypothesis. But if the significance level is 0.01, 0.0237 is greater than 0.01, thus we should fail to reject the null hypothesis. To find the p-value, we're going to use the standardized test statistic and then use our standard normal table or our t-distribution table, depending. Now in this section we're going to be looking at large samples and we'll be looking at the standard normal table. Remember, p is in the left tail for a left tail test, p is in the right tail for a right tail test, and p is split evenly, half of p in the lower tail, half of p in the upper tail for a two-tail test. Suppose the test statistic is negative 2.23 and it is a left tail test, then p is in the left tail or less than negative 2.23. You get your standard normal table. You look up the p-value at negative 2.23. Remember how you use the standard normal table. You look at the negative 2.2 along the far left column, and then you find the 0.03 along the top. See where that row and that column intersect, and we see in that case that the p-value is 0.0129. Since this is greater than 0.01, we fail to reject the null hypothesis. Now suppose we have a two-tail test and the test statistic turns out to be 2.14. Well, remember, in a two-tail test, p is split evenly between the two tails. So we can find this lower region using negative 2.14, which I think is a little easier to do. So let's use negative 2.14. Look it up in the standard normal table, and we see that that value corresponds to a value of 0.0162. If you look up 2.14, then you would have had to subtract 0.9838 from 1. If you look up negative 2.14, you would have gotten the 0.0162 right away. All right, and in this case, this is less than, so 0.0162 times 2, because we've only found half of it, so times 2 gives us 0.0324, which is still less than 0.05, so we should reject the null hypothesis. All right, now we use the z-test anytime either the population standard deviation is known or the sample size is at least 30. The test statistic uses the sample mean, and it is the sample mean minus the claimed value divided by the standard deviation divided by the square root of n. Recall, this is known as the standard error of the mean. But if n is greater than or equal to 30, then the sample standard deviation can be substituted. If the sample size is less than 30, we're going to see that in section 7.3, then we'll be using the t-distribution. So in order to use a p-value approach to do a z-test, the first thing we need to do is state the null hypothesis and the alternative hypothesis. We specify the level of significance and identify alpha. Then we calculate the test statistic. We use our standard normal table to find the area that corresponds. That's known as our p-value. And remember, for a left tail test, p is in the left tail. For a right tail test, p is in the right tail. And for a two-tail test, p is twice the area in either one of the tails. Then we make our decision based on the p-value relative to the significance level and interpret the decision in context of the original claim. So let's look at an example. Suppose a pit crew claims that its mean pit stop is less than 13 seconds. Less than does not include equality, so that means our claim is the alternative hypothesis, and the alternative and the complement of it is greater than or equal to, which is our null hypothesis. In this problem, it was stated that the significance level was 0.01. We then find the test statistic, which is sample mean minus the claimed value of 13 divided by the standard deviation, and that's divided by the square root of the sample size, and we get negative 2.98. Since this is a left tail test, we go to the standard normal, we look up negative 2.98, and we see that P is 0.0014. 0.0014 is less than the significance level of 0.01, thus we reject the null hypothesis, and our conclusion is, at the 1% level of significance, we have enough evidence to conclude that the mean pit stop time is less than 13 seconds. Let's try another example. Suppose the National Institute of Diabetes reports that the average cost of weight loss surgery is $22,500. Stands for equals. So in this case, the claim is the null hypothesis. We're going to randomly select 30 patients and find the average cost of their surgery is $21,545. That's going to be our X bar. And the sample standard deviation is 30.15. Because our sample size is at least 30, we can substitute the sample standard deviation and use the z-test. And we're going to use a significance level of 0.05. So our test statistic is the sample mean minus the claimed value divided by the standard deviation divided by the square root of 30. We get negative 1.73. That's down here. We look up negative 1.73 and we get a p-value of 0.0418, but that's only half the p-value because the other half is up here. So 2 times that is 0.0836. 0.0836 is greater than the significance level, so we fail to reject the null hypothesis, and our conclusion is, at the 5% level of significance, there is not enough evidence to support the claim that the cost of the bariatric surgery is different from $22,500. Now we're going to look at a different approach to a hypothesis test known as the rejection region or critical value approach. In this case, we look for a range of values for which the null hypothesis is probably not true, and we use the significance level to find this. So the first thing you need to do is specify the level of significance. Then decide whether the test is left, right, or two-tailed by looking at the alternative hypothesis. Then we find the critical values by finding the z-score. Now remember, what we're doing is what we learned in section 5.3. We're going to be given the probability, we're going to be given the area shaded, and in a left-tailed test we find the z-score that corresponds to that area of alpha. For a right-tailed test, we're going to find the z-score that corresponds to an area of 1 minus alpha. And for a two-tailed test, remember it's split half and half, so we split half of alpha on either side. Sketch the standard normal distribution, then find the critical values. Sounds much more complicated than it really is, so let's look at an example to see. Suppose we have a two-tailed test and a significance level of 0.05. Well, that means the 0.05 is split evenly into 0.025 and 0.025. So let's look up 0.025 in the body of the standard normal table. When we do that, we find that this corresponds to a z-value of negative 1.96. So our rejection region is to the left of negative 1.96 because it's a two-tailed test, and to the right of positive 1.96. Then our decision rules is based on the fact of where does the calculated test statistic fall. If it falls inside the rejection region, then we reject the null hypothesis. If it is not in the rejection region, then we fail to reject the null hypothesis. All right, so in a left-tailed test, this is the rejection region, and here we would reject the null hypothesis. If it falls in this area, we would fail to reject the null hypothesis. In a right-tailed test, the rejection region is in the right tail. If the test statistic falls in the right tail or in the rejection region, we reject the null hypothesis. If it does not, we fail to reject. And again, here our rejection regions are split between the two tails. If it falls in either rejection region, we reject the null hypothesis, but if it falls here in the middle, we fail to reject the null hypothesis. So to use the rejection region approach, the first step is still the same. We still state the null and alternative hypotheses. Then we identify the level of significance. Then we sketch the sampling distribution. Is it a Z distribution or a T distribution? We determine the critical values by using table 4, which is our standard normal table. From that, we determine the rejection regions. Then we calculate the test statistic. If the test statistic falls in the rejection region, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And then interpret the decision. So now let's look at an example, testing with rejection region approach. Suppose the employees at a construction claim that the mean salary is less than $68,000. Less than does not include equality, so in this case, our claim is the alternative hypothesis. They go take a random sample of 30 and find that the average salary of those 30 is $66,900 with a standard deviation of 5,500, and we want to use a significance level of 0.05 to test the employee's claim. Now recall, the claim was the alternative, so the complement of it is greater than or equal to 68,000. Since our significance level is 0.05 and it is a left tail test, then 0.05 is down here. We look up 0.05 in the body of the standard normal table and we find that the critical value is negative 1.645. We calculate the test statistic, which is negative 1.10. Negative 1.10 is over here somewhere. It is not in the rejection region. This is our rejection region. It's not in the rejection region, so we fail to reject the null hypothesis. So at the 5% significance level, there is not enough evidence to support the employee's claim that the mean salary is less than $68,000. Let's do another example. Suppose the U.S. Department of Agriculture claims that the mean cost of raising a child is $13,120. Is stands for equals, which means our claim is the null hypothesis. They randomly select a sample of 500 children, and from this sample of 500 children, they find the mean cost to be $12,925 with a standard deviation of 1,745. Let's use an alpha or significance level of 10% to test this claim. So because it is 13,000, the claim was the null hypothesis. The complement of equals is not equal to. The significance level was 10%. So if we had, since this is a two-tail test, we split this 10% in half. 5% in the lower tail, 5% in the upper tail. We look at 0.05 in the Z table, in the standard normal table, and we see that it is negative 1.645. By symmetry, that means this value appears positive 1.645. The test statistic turned out to be negative 2.50, which is inside the rejection region. So we reject the null hypothesis. At the 10% significance level, we do have enough evidence to conclude that the mean cost is $13,120. That's the end of section 7.2. You have quite a few problems you can try to see how well you understand this material at the Course Compass My Math Lab website under Homework 7.2.